Imagine you have a binary string like 111000, and your goal is to turn it into an alternating binary string like 010101 or 1001010. But here's the twist. You're allowed to rotate the string and flip characters. Now the question becomes, what is the minimum number of flips needed? This is problem 1888. Minimum number of flips to make the binary string alternating on LeetCode. And the trick to solving it efficiently is something many candidates completely miss. In interviews, let's break it down. We are given a binary string S. We can perform two operations. Operation 1, rotation. Move the first character to the end. Example, 111000 becomes 110001. Operation 2, flip. Change 0 to 1 and 1 to 0. Our goal is to make the string alternating. Alternating means 010101 or 1001010. Now here's the key observation. For any length n, there are only two valid alternating patterns. Pattern 1, 010101. Pattern 2, 1001010. So the real question becomes, for every possible rotation of the string, how many flips do we need to match one of these patterns? A naive solution might try this. Step 1. Rotate the string n times. Step 2. For each rotation. Step 3. Compare with both alternating patterns. That leads to O of n squared. And for strings up to 100,000, that's way too slow. So we need a smarter idea. Here's the trick most people miss. Instead of rotating the string, we can simulate all rotations by doubling the string. Example, S equals 111,000. S plus S becomes 111000111000. Now something magical happens. Every possible rotation of the original string becomes a substring of length n inside this doubled string. So instead of rotating, we just slide a window of size n across the doubled string. And this is where sliding window comes into play. Next step, we generate two ideal alternating strings. Pattern A, 0101010101. Pattern B, 10101011010. Both patterns have the same length as our doubled string. Then, while sliding the window, we simply count the mismatches. For example, if our window is 111,000, compare it with 010101. Count the mismatches, then compare with 101,010. Take the minimum. As the window slides, we update the mismatch counts efficiently. This makes the algorithm linear time. Step 1. Double the string. S equals S plus S. Step 2. Create two alternating patterns. Step 3. Use a sliding window of size n. Step 4. Track mismatches with both patterns. Step 5. Keep updating the minimum flips required. Time complexity becomes O of n, which is perfect for large inputs. Now let's walk through the code. We start by defining the function minimum flips. It takes a binary string s as input. First, we store the length of the string in a variable called n. Then we double the string. S becomes S plus S. Next, we create two empty strings. These will store the ideal alternating patterns. Pattern 1 starts with 0, 010101. Pattern 2 starts with 1, 1001010. We build these patterns using a loop over the doubled string. If the index is odd, pattern 1 gets a 1 and pattern 2 gets a 0. Otherwise, pattern 1 gets a 0 and pattern 2 gets a 1. Now we initialize our sliding window variables. We track mismatches with both patterns using diff1 and diff2. And we start the left pointer at 0. Next, we slide a window across the doubled string. We track mismatches with both patterns using diff1 and diff2. And we start the left pointer at 0. Next, we slide a window across the doubled string. For every character we check if it matches the expected value in pattern 1 and pattern 2. If it does not match, we increase the mismatch counter. If the window becomes larger than the original string length, we move the left pointer forward and subtract the mismatch that leaves the window. Whenever the window size equals n, we compute the minimum between the two mismatch counts. That value represents the number of flips required for this rotation of the string. Finally, we return the smallest value found. That is the minimum number of flips needed to make the binary string alternating. This problem tests three key concepts. First, recognizing alternating patterns. Second, using the string doubling trick. Third, applying sliding window optimization. If you immediately think, rotation problems can often be solved with string doubling, you're already thinking like a strong algorithmic engineer. If you enjoy learning LeetCode patterns, interview tricks, and deep DSA intuition, subscribe for more breakdowns. Next, I'll show you a problem where sliding window and greedy combine in a very unexpected way. See you in the next one.